Do I start now? Or? Oh, yeah.
Hi everyone, now we have Phil talking to us about contracts. Once again, submit questions online if you don't want to submit them in person.
Hi, so I'm Phil Nguyen presenting our work on soft contract verification for higher order stateful programs. This is joint work with David Van Horn, Sam Tobin-Hochstadt, and Thomas Gilray. This is an example in Racket of a function that remembers and returns the largest natural number that it's seen. To enforce its behavior as well as correct usage, a programmer can attach to it a contract which can be composed from arbitrary Racket expressions and can make use of Racket's full expressiveness. In this example, it's a simple dependent function contract that ensures that f only receives natural numbers and only returns one that's no less. The semantics of contract monitoring at runtime ensures that if any party violates any part of the contract, then there's a blame that's raised that with detailed information pinpointing the exact source of error. Despite expressiveness and flexibilities, contracts as runtime checks have obvious downsides that deter some programmers from using them to the full extent in practice. They introduce significant overhead and delay error discovery late until runtime when there's an actual violation. Verifying ahead of time all or most of the contracts would eliminate these downsides and give programmers the strong guarantees of static checking as much as possible without giving up the original flexibilities of contracts. Occasionally, unverifiable contracts can just be left as is for dynamic checks with the existing familiar semantics. There's been previous works by others and us on doing such verification for pure functional programming languages. But practical languages have mutable states, and it's important to be able to handle such feature well in order to scale to realistic programs. In this work, we present a sound and modular contract verification for higher order stateful programs. For the rest of the talk, I'm going to go briefly overview of the unique challenges in verifying contracts, especially in the higher order imperative settings. Then I'll present the key points in our solution using higher order symbolic execution. Then I'll give an intuition of its soundness, which has been mechanized. Then I'll discuss evaluation and limitations. So what usually make contracts pleasant for programmers to use are also the things that make it difficult to verify them effectively ahead of time. In particular, contracts are arbitrary expressions that are capable of reading and modifying states and crashing and diverging. They're also values that are composable in the first-class way. Contracts' expressiveness prevent them from being readily translatable to, say, first-order formulas for S&T solvers to discharge. Another difficulty comes from the idiomatic usage of contracts and dynamic languages in general. For example, programmers tend to rely heavily on path-sensitive interprocedural reasoning in order to justify the correctness of their code, and contracts are just boundaries, which makes it hard to reason about programs compositionally. For example, contracts are not necessarily loop invariants, and the programmer can temporarily modify the state to be inconsistent with the contract, as long as the state is consistent whenever it is read by an outside party that the contract is established with. Another difficulty in sound reasoning about higher order stateful programs is that an arbitrary function flowing from an unknown context can have a wide range of behaviors. For example, it can store a reference to an effectful function and invoke at an unintended point. Our approach to address these problems, these challenges, is a simple operational method based on symbolic execution, extended to allow symbolic values that are higher order. To verify a module, we simply run it in a modified semantics that allows incomplete programs with holes. And the contracts mediate values that flow into and out of these holes. For the rest of the talk, I'm going to call the rest of the program that's not the holes, the transparent part of the program, which is the part of the program under verification. We ensure that our modified semantics is sound in the sense that if any instantiation of the holes would cause a blame on the transparent part of the program, then the modified semantics discover the same blame. As a consequence, a run without any error is a full verification. We previously established this result that verified module can't be blamed for pure functional programs, and in this work we extend it to continue to hold for higher order imperative programs. So higher order symbolic execution builds upon traditional standard first order symbolic execution, which given a language extends its value set with symbolic values, which may stand for any standard value. The semantics is then extended with non-deterministic rules to account for all possible values that symbolic values can stand for. For example, comparing a symbolic value bullet sub 1 with 4, if a conditional branching on that takes both branches because we don't know anything about the symbolic value, then there's a path condition that accumulates facts that must hold about symbolic values in order for symbolic execution to reach each branch. The path condition is then useful for pruning infeasible paths and proving that certain results are not reachable. For example, if a symbolic value is greater than 4, then it should be safe to divide by it. So higher order symbolic execution generalizes that by allowing symbolic values to also stand for functions. The obvious question is then what to do when applying a symbolic function. If this was a concrete function, then execution simply jumps the function body. So it's clearly impossible to literally simulate all possible function bodies there are. Before I describe the rules, let me state the high-level goal informally is to discover all possible interactions between the caller and the unknown function, in particular all possible errors on the transparent part of the program and all possible states that the caller can be brought to by invoking an arbitrary function. We'll revisit later what it means to have a sound over approximation. So the obvious thing, the first attempt is to let the symbolic function just return a symbolic answer. This is not enough because in a higher order setting, a function interacts with its surroundings not only through the value that it returns, but also through what it supplies to its argument, if the argument is a function. For example, if we apply a symbolic function to a function that divides by its input, simply returning something would unsoundly miss the division by 0, blaming on the transparent part of the program. If the function applies its argument to 0 as an example. So to fix this, we, in addition to returning something, also applying the argument to a symbolic value and put the result back into the unknown context to simulate arbitrary interaction with the result. If this was a pure programming language, this would be enough. In fact, it's a previous result on sound symbolic execution of higher order functional languages. In the presence of mutable states, however, states are another channel of communication between the caller and its callee. In this example, the caller initializes its state to be -3 and passes a thunk that increments x and divide by x. It takes 3 invocation of this thunk in order to trigger the division by 0. So in order to approximate that, we also let the symbolic function simulate an arbitrary number of times of invocation of any function that flows to it. This is not yet enough, because the unknown code has an option to store any value that flows to it and invoke at a later point. In this example, each thunk is safe to invoke an arbitrary number of times on their own, except for the fact that the unknown code could have saved the thunk that divide by x and invoke later when it has incremented x with enough number of times. So to approximate this, we keep around in the store, which is the blue square on the slide. We keep around in the store a special address that keeps track of values that have leaked to the unknown context. And whenever we transfer control to the unknown, we simulate, we non-deterministically pick a value that has leaked to the unknown context and invoke it an arbitrary number of times. So in summary, whenever we apply a symbolic function, we remember that the argument has been leaked, and we non-deterministically pick a value that has leaked to invoke it and simulate arbitrary interactions with it, in addition to returning something. So there are two questions that arise. Is it sound because we're using a finite number of rules to approximate arbitrary code? And is it practical because the branching factor seems to be pretty high? To address the first question, let's look into the definition of what it means for a symbolic state to approximate a concrete state. For base values, it's straightforward. We also let a blame on the transparent part of the code approximate itself because we care about blame on the transparent part of the code. In contrast, we don't care about blame on the unknown part of the code. Most of the cases are straightforwardly structural. One non-trivial question is, what does it mean for a function to instantiate a symbolic function? Because we already distinguish between blames on the transparent part of the code versus blame on the unknown part of the code, it makes sense to distinguish between code that comes from the transparent part of the code and code that comes from the unknown. And we encode that explicitly in the approximation relation. For example, 1 divided by 0, annotated by source location transparent, is a distinct piece of code from 1 divided by 0 coming from the unknown. And when the control component of a state comes from the unknown, we let it be approximated by a symbolic application. Finally, we index the approximation relation with an abstraction map to keep track of the approximation between the stores. For example, so the abstraction map maps each address from the concrete state to an address in the symbolic state that approximates it. So this definition is enough for us to prove a main lemma that the modified semantics, its small step, preserve this approximation relation. In particular, if there's an instantiation to the symbolic state that makes progress to another state, then the modified semantics in 0 or more steps continues to approximate it. The proof is by straightforward, although tedious, case analysis on the reduction and the approximation relation. It's been mechanized in Lean. The intuition is that the only non-trivial case is when the symbolic state applies a symbolic function and the instantiating state applies a function with code coming from the unknown. When control from the concrete state continues to stay in the unknown, then the same symbolic application continues to approximate it. And we index the approximation relation with enough information to ensure that whenever control transfers back to code from the transparent part of the program, which it can only do so either by returning or applying any of the leaked value, then there's one rule in the modified semantics that ensures that the next state continues to approximate it. So to evaluate our work, we implemented a verifier for core racket and rely on a previous pass of macro expansion to take care of language features that are not primitives, such as pattern matching, loop comprehension, and various domain-specific languages. We straightforwardly implemented the first-order primitives by systematically lifting brackets implementation for the concrete cases and attach enough contracts to make sure that the symbolic cases are adequately precise. There's no systematic way to lift higher-order functions, higher-order primitives and library functions to the symbolic execution, but we found out that in most of the cases with simple contracts, especially higher-order, especially parametric contracts, are enough to constrain the behavior of unknown functions to get the kind of precision that we want. For example, if we call with input file with a second argument being a function that only returns 6, then symbolic execution is able to prove that call with input file will only ever return 6 because 6 is the only value that's ever wrapped in the seal alpha. We also integrated an SMT solver. The details are in the paper, but the simple story is that we still rely mainly on the operational semantics to take care of language features like higher order functions and side effects, and only pass first order formulas on base values to SMT solvers for sophisticated reasoning. We evaluated our work on a bunch of benchmarks from previous work, ranging from higher order model checking and previous different type systems, and also many modules from real bracket code bases. The summary is that we get reasonable verification time with low false positives. In general, the total count is about 40,000 something checks, and we get 20 something false positives. The largest module is about 2,000 lines and took 20 minutes to verify. Most modules are in the order of 100 to 300 lines and take about 10 seconds to verify. So as we've seen before, the rule for applying symbolic function is pretty problematic in its branching factor, but it turns out not so bad for mostly functional programs because the state space gets fixed pretty quickly. If we were to verify highly imperative programs where a lot of functions are leaked to the unknown, then we would have needed more help from either a more precise contract system that keeps track of functions effects, or by manually breaking down a program into many smaller modules. So one particular pattern that's fairly common in dynamic programs that we could not handle well is when a module has control over the instantiation of the structs that it defines. Outside of the module, a cheap tag check would imply deep structural property about the value. For example, that a value is a node implies that it's a non-empty proper tree. So to help verification go through, the programmer needs to change the cheap tag check to a complete contract. Depending on your point of view, this is not that bad of a limitation because this is the invariant that the programmer has in mind in the first place. This is an optimization from manually analyzing the program. And the premise of the tool is that when it's good enough, the programmer gets to write expensive, expressive contract without worrying about performance implications. But anyways, being able to efficiently reason about such kind of pattern is an important improvement in future work. Another improvement that we're working on is allowing programmers to enter terms as manual proof guides, because the one consequence of trying to automate everything is that the verification result is sometimes unpredictable. You modify the program a little and you can't verify it doesn't go through anymore, or it takes a long time to finish. So in conclusion, higher order symbolic execution allows modular and sound verification of higher order stateful programs in its scales, and you should check out our work.
Hey, so another type that's usually challenging to handle in imperative higher order verification is pointers or references.
Yeah.
Because if I leak a reference to unknown code, it can now mess with everything that's transitively reachable. Is that something you handle, and how?
Okay, so are you asking about mutable boxes or something?
I don't know anything about Racket, but
Yeah.
yes.
Okay, so in Racket there's no pointer, and in the formalism we encode everything as lambdas. We encode mutable boxes as closures, and we have this property where, in order to cause side effects that matter to the transparent part of the code, we have to first transfer control to the transparent code, and it soundly proves that. But I guess your question is about pointer manipulation programs, which Racket does not have pointers.
Okay, I may bother you later. Thanks.
Yeah.
There's a question from the internet. It is, I didn't understand your change to the semantics to accommodate the approximation relation. Could you clarify?
So, I mean, the question is a little vague to me.
Maybe you point them to where the approximation.
Yeah, so
Could you repeat the question?
So the question is, they didn't understand how I changed the semantics to accommodate the approximation relation. I mean, I'm not sure, like, concretely what the question asked about. Can I? Yeah. Yeah, later.
With the tree predicate versus contract, structural contract example, could you maybe with a hint from the programmer check using your framework whether the tree predicate implies the contract, and would that be useful?
So your question is whether I have like hint to the programmer to change from the tree ha to tree /c?
Right. So instead of doing that, could you say, by the way, I believe that the tree predicate implies this other contract holds for all things in this module?
So we're not doing anything like that.
Okay.
Right now.
Yeah, my question is on basically the same thing. So it's known that switching to these big structural contracts can result in asymptotic regressions in efficiency behavior.
Yeah.
So are you actually able to remove that tree C in your analyses? If I had, say, BSTs, could you verify that everything produced by my abstractions were appropriate BSTs?
So verification is like a separate issue. So the story is that it's trivial to throw away the positive components of the contract, but the tree is a negative component, and it depends on each call site. And I don't think in Racket we have we currently easy to at each call site pick which contract to throw away from the reference that we call from. So verification is a different issue.
But would it then be correct to conclude that the changes necessary for the contract analysis to work would result in a performance regression in the code being analyzed?
On what?
So it seems to me then that for your analysis to work, you need to change to use these less efficient contracts.
Yes, for now.
So therefore, the version that can be analyzed is a less efficient version of the
Yes.
code, and developers would have to manually choose to run a more efficient version that was not analyzed.
Yeah, but when there's enough facility to flexibly throw away the contracts from the call site, then it's doable.
Okay, so then, I'm sorry to take up too much time, but my core question is, okay, so in what settings can you actually get rid of those? Could you do binary search trees?
Um,
We'll do it offline, don't worry
okay,
about it.
yeah.